Okay, so the other reason that we need to know Kirchhoff rule is because we want to analyze what we call the RC circuit. The RC circuit, like the name suggests, is a circuit consists of R and C. So it's a circuit that consists of one, for us now, well, the simplest is one R and one C, one capacitor. So one resistor and one capacitor. And we want to analyze the behavior of this kind of circuit. So this is called the RC circuit. Okay. A capacitor is something that we discussed last time. Remember, the role of capacitor is to hold charge. When it's charged, then you can store some charge on the two ends of the capacitor. So if you don't remember, let me remind you that capacitance C for a capacitor is defined to be the amount of charge divided by the potential or the voltage across the capacitor. So let's look at a generic situation when you have a capacitor. So the symbol is like this, right? So it looks like a battery, but the capacitor has the same length on both sides. Unlike a battery is something like this. Okay, so one side is shorter. So don't get confused. So this is a capacitor, and when you put some charge on the capacitor, again, you cannot just put in charge out of nowhere. Usually you have to move it from somewhere. And the easiest place to get that charge is to move it from one side to the other side. And that's why we always write the charge to be plus Q on one side and minus the same amount on the other side, like this. Okay, so this Q is what we mean by Q in this equation. All right. So don't double count it, because some of you might think, okay, it's plus Q here, it's minus Q here, so it's a total of 2Q. It's not like that. Okay, when we say it's Q, then it's just one side, right? So the other one is automatically minus of the same amount, which is minus Q. Okay, and the voltage delta V here, the voltage difference, it means that if you take a voltmeter and then you measure the voltage across the capacitor like this. Okay, so what you read in this voltmeter, so see, this is the same way that we measure the voltage across a resistor or voltage across a battery. Right? So it's measure how much potential this point here is larger than this point here. So what you're going to see is delta V that appears in this formula. So delta V is going to be Q divided by C. So in other words, the voltage across the capacitor is a direct measure of how much charge you have on the capacitor. The more charge you have on the capacitor, the more voltage difference, potential difference between the two legs or the two terminals of the capacitor. All right? And a capacitor in this sense acts like a battery, meaning that if you connect this capacitor to a resistor to complete a circuit, then there will be a current flowing like this. But the difference is that when you have the current flow, I here, what is the current? Well, current is the movement of charge. When you have charge flowing out, you're going to have less charge on the capacitor. So the voltage will be less and less. This is the main difference between a capacitor and a battery. A battery will always maintain a fixed potential difference between the two terminal, where the capacitor is not going to be fixed because it depends on how much charge you have. If you have less charge, then the potential will be less. Okay, so that makes the circuit a little bit more dynamic because it's not just a boring constant current throughout every element in the circuit, but you're gonna have something that depends on time, and that's what we want to do for the remaining time of this lecture. Okay, to see how current changes with time in a circuit where we have a capacitor and a resistor. Okay, so let me just write down the key point again here. So as I is the current, as I flows, Q on C decreases and I will change with time. Okay, so if Q on C decreases, then the voltage across the capacitor also change. Unlike a battery like this. Okay, so a battery, so for the battery, delta V is fixed. So I, the current, does not change with time. That's the difference. Okay, and the battery, the way it works is kind of completely different from the way capacitor works. A capacitor is just storing charge and then you just take it out when you need it. But a battery is done by like chemical reaction, so it's entirely different process. So that's why the behavior is also very different. Although in the circuit, sometimes the purpose of a capacitor and the purpose of a battery is kind of the same, which is to provide energy to the circuit. Okay, anyway, let's analyze the simplest case of RC circuit. And this is what we're going to call discharging. Discharging C. And we're going to talk about charging C in a moment, but that's more complicated because we need 3 elements in that circuit. Where this one, you only need 2. So let's set up the problem like this. So we have a capacitor, charge. How do we charge it? We don't care. Someone charge this capacitor up so that it has charge Q on plus Q on one side and minus Q on the other side. Okay, and if you don't do anything to this capacitor, ideally, then the charge will just stay there forever. But in real life, you're gonna have like charge leakage, like believe it or not, like electrons can just jump through the air, even though it's very small amount. But you're gonna have charge slowly decaying. But ideally, that's not gonna happen. The way you can take out charge is to complete the circuit. So we need another element in the circuit, like this capacitor, like this. And our goal is to analyze the current flowing in the circuit like this. And again, this current will depend on time. Because we don't have a battery here, we have a capacitor where the voltage across the capacitor also depends on time. Okay, so I here, I say I as a function of time. All right, so let's look at how we gonna analyze this. So we're gonna use Kirchhoff rule, especially the loop rule. And we're gonna walk in the circuit starting from this point. And our loop is to start from here, go around, and then come back here, like this. So the first element that we encounter is this resistor. So applying the loop rule, we're gonna have the first element, and we are walking in the same direction as the current, so it's gonna be the minus sign, so it's gonna be minus I. It's a function of time, but I'm not gonna write that now because it's to make everything clean. So minus IR, and then when we walk across the capacitor, now in this case the capacitor is acting kind of like a battery. So it's going from negative to positive terminal, so you have to do the plus sign here. So it's plus V across the capacitor, so I write VC here, and that's equal to 0. Okay, so even though I wrote this using loop rule, but this looks very similar to just applying the Ohm's law, right? V equal to IR, and it's not wrong to look at it like that. But if possible, I don't want to look at this as simply applying the Ohm's law, because I think the Ohm's law usually valid for the case where the potential V is a constant. In this case, not, but we apply it anyway, and it's not wrong. But I think conceptually, it's better to start talking about this using the loop rule, like what we have here. Okay, so mathematically it looks the same, but in terms of the interpretation, it's a little bit different. But that's just the minor points that I want to point out. But it doesn't really matter, because in the end we just have VC equal to IR. Okay, so now let's do a little bit more to this equation. What can we do? Well, VC is the voltage across the capacitor, right? So obviously it's a function of how much charge you have on the capacitor. So I can replace this VC by Q divided by C, right? Using this equation here, right? That's actually the definition of the capacitor, so there's nothing to argue with. And remember also that these variables that I'm highlighting with blue, these are what depends on time. These are not constant. Okay, I depends on time. Q, the charge on the capacitor, also depends on time. Okay, but R and C are fixed by the capacitor and the resistor. Okay, so on the left hand side we have Q over C, and then it has to be equal to IR. Now what is I? If you remember the definition of I, what is I? Well, I is the flow of charge over time. If you want to be, super precise, in the case of, non-steady flow of the charge, you have to look at instantaneous flow. So it's going to be the derivative of the charge over dt like this. Okay, so it's dq by dt essentially. That's what the current is. And normally we talk about the case where the current flow in the circuit is it's fixed, doesn't change. But in this case, it does change with time. So we actually need to write it in terms of derivative like this. Okay, so I can write dq by dt. Actually, I want to put r in front maybe, because just to be clear that r does not go inside the derivative, so you have something like this. Okay, but this I here transform itself to dq by dt like this. But there's something wrong here, because you can see that the way that current flowing here, the direction that we choose, is actually flowing out from the capacitor. So if you look at this, when the current flow, the charge on the capacitor must decrease. So we need a minus sign here. Okay, so this minus sign is because of our choice of the direction of the current. Okay, so we choose to call the current to flow in this direction, and that's going to be consistent with decreasing the current on the capacitor. Okay, so there's nothing wrong with this. You can say that, okay, how can this be? Because the definition of the current is like that. Well, sure, that's true, but I can also, I have a freedom to call the current flowing one way to be positive and the other way to be negative. Okay, so that's why we need a minus sign here. If for whatever reason you choose the direction of the current to flow the other way around, like to flow this way, then you don't need a minus sign here, right? So it's kind of like, it's your choice, right? It's kind of like when you solve the mechanics problem, you call like going down to be positive or going up to be positive. You have that freedom, but you have to be consistent, right? And this minus sign is there because of the consistency of our choice. Okay, so we need this. And then you can see that if we don't put a minus sign, then the circuit gonna behave in a very strange way. So we need a minus sign here. Okay, so we have here kind of a differential equation, and I'm not sure if all of you have studied, or taken the class in differential equation, but this is kind of a very simple case, so don't freak out if you have not done any differential equation, because in this case you just integrate the problem, the equation, and then you get the result. So it's going to be a little bit mathematical. So let me write it in a more kind of systematic way. So it's going to be very clear by writing that Q is a function of time divided by what I actually, okay, let's leave it like this first. C equal to minus R dq by dt. Okay, so this is what we call a differential equation. So essentially it's an equation that involves the derivative of a function, and our goal is to find the function that solves this equation. Okay, so it's unlike a normal equation where you find the value of the variables. In this case, you find the function q that solves this equation. Okay, so it's a differential equation, and in a little bit more advanced course, you're gonna have like integral equation where you need to find the function that solve an equation that involves the integral of the equation, something like that. But anyway, so let's try to solve this. The way to solve this differential equation is just to put the things that belongs to the same variable in the same side and put the other things in the other side. So what do we have here? Well, we have terms that depends on Q, which is what I label in green here. So we want to put these green things in the same side of the equation and put everything else to the other side. So that means what I have is dt, well actually minus 1 over RC dt on one side. So this is the blue stuff. And this equal to the green stuff, which is 1 over q dq, like this. Okay, so just put the things that belongs to the same kind of, the things that contains the same variables on one side, and then the rest on the other side. And then you just need to integrate this. So you need to integrate this equation, and 1 over RC is a constant, so you can take it out of the integral sign. But on the right hand side, you need to integrate the whole thing because Q is not a constant. So you have to do this. Okay, and you need to put in the limit of integration. So you're going to integrate time from t equal to 0. So you integrate from t equal to 0 to any generic time. And you're going to integrate the charge from the time equal to 0. Now the time equal to 0, there's going to be some charge on the capacitor. So that's what we call the initial charge, right? For example, at t equal to 0, there might be like 1 microcoulomb of charge on the capacitor. And then as time passes, then that 1 microcoulomb will become less and less. So I'm going to write Q, which is Q at t equal to 0, to be equal to what we call Q0. So that's the initial amount of charge. Q0. And then we're going to integrate it to some later time, which is some, time later, which is Q at some later time, QT, like this. Okay, and now the integral is actually not that bad because on the left hand side it's just a constant, and the right hand side is going to be the natural base of logarithm function. So let me copy this so that you see. So go to the next page here. So this one, okay. So you're gonna get minus 1 over RC. No, integral of nothing, you get the variable t. And then the way I would write it is to use the bracket to put in the limit of integration. So t equal to 0 to some other time t equal the right hand side, which is integral of 1 over q dq. So if you know, it's integral of 1 over x dx gives you log of x, right? So this is log base e of x. Okay, e is 2.7128, something like that. So you're gonna get log of q, and then you're gonna substitute q 0 to any time, q at any time, like this. So let's put in the limit of integration. So you're going to have minus t over qc equal to log of q as a function of time minus log of q0, like this. Okay, and log, the difference of log is the log of the ratio. So you can use the identity to write qt divided by q0. Okay, and this means I can exponentiate both sides. So what I get is e to the minus t over rc equal to qt divided by q0, or in a more familiar form, q as a function of time is q0 times e to the minus t over rc. So we have solved this differential equation because we have found the function of the charge as a function of time that solves that equation, differential equation that we had before. Okay, so it's e to the minus time divided by something. This is what we see a lot, not just in physics, but in almost every branch of science that involve differential equation, because this is what we call exponential decay. And I hope this is not the first time you have seen this. This is exponential decay. And sometimes this RC thing, we rewrite it using the variable tau, which is called the time constant. So in other words, we can write this also in this form, which is Q0 equal to e to the minus time divided by a time constant tau, like this. Okay. So the time constant, which depends on RC in this case, is just a parameter that tells you how slow or how fast the decay is going to be. So in this case, if you, and then choosing different value of capacitance or resistance will give you different amount of tau. So if you plot the charge as a function of time, we can, right, because we know how it behaves, right? So it's gonna start at the initial value, and you can see that the initial value is indeed Q0, because if you take t equal to 0 here, e to the 0 to the power of 0 is 1. So at time equal to 0, then the charge is Q0. So that is independent of the time constant, which what it should be, because the initial charge is what we choose. It's nothing to do with RC. So it's gonna be always starting at Q0 here, right? So if you have really large time constant, so it's gonna decay slower. So the graph gonna look like this. So maybe at some generic time constant, it's gonna decay like this. So let's say this is medium tau. Now what happens if you have tau, the time constant, to be very small? If you have tau to be very small, then you are dividing with by a small number. So it's e to the negative large number, so it's gonna decay really fast. So for a small time constant, you're gonna have fast decay. So this is small tau. And if you have large value of tau, then it's gonna decay very slowly. So it's gonna go something like this. This is large tau. Okay, so it's kind of like telling you how fast this decay is going on. Okay, so in this case, at this point, maybe it's easier to just look at some example and get some idea of what's going on. So let's just calculate the time constant for a very generic value of resistance and capacitance. So as an example, so suppose we have a discharging RC circuit, which is given by R equal to 1 kilo ohms, which is 1000 ohms. This is a very generic, very common value of resistor. Okay, 100 ohms, 1 kilo ohms, something like that. And a generic value of capacitor is about, let's say, 10 microfarad, which is not big, not too small. And this is in farad is 10 to the minus 5 farad, like this. Okay, so what's the time constant? Well, tau is just R times C. So if you calculate R to be 1000 and then C to be 10 to the minus 5, so you're going to get this to be 0.01 second. So it's 10 milliseconds. That's the time constant. Okay, so this time constant tells you how long you have to wait until the charge kind of disappear from the capacitor. For example, if we have Q0, the initial charge, to be, let's say, 10 microcoulomb. So what is charge at 10 milliseconds? Well, obviously, it's going to be less than 10 microcoulombs, right? Because some charge going to leave the capacitor. Okay, but how much exactly? Well, Q0 t, q as a function of time is q0 times e to the minus t divided by tau. Okay, and at time equal to 10 millisecond, we can just substitute into this equation. So the initial charge is 10 microcoulomb. E to the minus t, which is 10 millisecond, divided by the time constant, which is also 10 millisecond. So 10 millisecond and 10 millisecond cancel out. So it's just minus 1. So that means I can write Q at t equal to 10 millisecond is the initial charge, which is 10 microcoulomb, times e to the minus 1. Now, e is about 2.718 or something like this. So this means is 10 microcoulomb divided by 2.718. And you get about 3.7 microcoulomb. Right. So after 10 millisecond, which in this case is just one time constant, you are left with about 37% of the initial charge. Okay. So what happens if you wait for another 10 milliseconds? Let's say you have t equal to 20 milliseconds, right? So it's going to be 10 microcoulombs times e to the minus 20 millisecond divided by 10 millisecond. So that's going to be 10 microcoulomb times e to the power of negative 2. So you can see that you divide by another factor of e. So every time you divide by a factor of e, you are left with only 37% of the initial value. So if you do it twice, then you have to divide by 2.718 square. So that's going to be about 1.37 microcoulomb. So every time you wait for another time constant, then it's going to be reduced by another factor of e. And this is very similar to, some of you might, I don't know whether you have studied this, about, like the half-life decay of, radioactive stuff, right? So you know what the half-life is? Half-life is the time you have to wait such that the initial amount of radioactive is left, is reduced by half. So another half-life, then you get another half. Right? So it's always half, half, half. So you get very close to zero very fast because of the nature of the exponential decay. For example, if you wait for 1 second, which is actually not long at all, right? 1 second is like 1, 2, and then that's 1 second. But after 1 second, you're going to see that the charge almost gone because its initial charge e to the 1 second, which is 1000 millisecond, divided by 10 millisecond, which is the time constant. So it's going to be 10 microcoulomb times e to the minus 100. And if you calculate this on your calculator, you're going to get that the charge is 10 to the minus 49 coulombs. And it's so small that we can say it's 0. Because, at this point, no device is going to be able to measure this small amount of charge. Okay, so mathematically, it's going to be very close to 0. It's not exactly 0. It's going to be, like 0.00001 or something like that. But in physics, you cannot measure this small, so you can say that, okay, all the charge has disappeared from the capacitor. Okay, so that's the charge on the capacitor. Now, we can also write down the expression for the current, because if you go back a little bit, you can see that we have this relation between current and charge, right? So if you want to know the current, you just find the derivative of the charge with the minus sign, of course. Okay, so let's remind ourselves again what's the circuit that we have. So we have a capacitor with initial charge to be Q0 and then minus Q0 on the other side. And you have a resistor here, R here. Okay, so it's the same circuit, I just redraw it. But now we know that Q as a function of time is Q0 times e to the minus t over the time constant tau, and the time constant tau is R times C. Now we want to know the current. So the current is, again, our choice of calling this current to flow this way force us to put a minus sign in here. Otherwise, it's not consistent. So it's minus of d by dt of q as a function of time, which is pretty easy to calculate because the derivative of the exponential function is the exponential function itself. So you're going to have minus q0 because that's the constant. And when you do the differentiation, then you have minus 1 over tau goes in front, and then you have minus t over tau like this. And the minus sign cancel out. We can restore tau to be RC. So it's Q0 divided by RC times e to the minus t over tau like this. And in a similar fashion, we can also call the factor in front here to be the initial current, because that's the current that you have at time equal to 0. So it can be like this. IT like this. So the current also decays exponentially, right? Which is, I think that's not totally surprising. And eventually the current will be 0 because eventually you have no charge on the capacitor. So the current has to be 0. Okay, but the interesting thing is I0, which is I at t equal to 0. So if you look at this, the way we define it, I is the current at t equal to 0 is just Q divided by RC, right? But what is Q0 divided by C? Well, that's the voltage across the capacitor at time equal to 0. That's the initial current. Okay, so this also kind of consistent with Ohm's law because like at time equal to 0, no charge has left the capacitor, right? So right at that moment, the capacitor behaves, or at least at that exact moment, like a battery with the voltage given by Q0 divided by C. That's the definition of the capacitor, right? And then you can use V equal to IR to calculate the current. But again, the main difference is that as time passes, the charge will be less and less. So the potential across the capacitor will be also less and less. So I will decay exponentially like this. Okay. So that's discharging the capacitor. The next thing we're going to do is, well, to complete the discussion is to talk about how do we charge the capacitor. So next going to be charging a capacitor. And to charge a capacitor, you need to have some, like power source somewhere or a battery somewhere. So the simplest case is to have the third element in the circuit, which is a battery. So it's going to be a little bit more complicated, but there's nothing we can do about that. So we have a battery which is fixed at V0. And we have a capacitor here, and we have a resistor again here. You might be wondering, like, do we really need a resistor here? Well, the answer is yes, because you might think that we maybe don't need it. Can we just connect the battery to the capacitor, directly? But you still need resistance in the circuit, because otherwise um, strange stuff gonna happen. And in reality, you also cannot just simply connect a battery directly to a capacitor, saying that there's no resistance in between. Because if you use any wire at all, you're gonna have some resistance. It might be small, but it's not gonna be zero. Okay, so you need to account for that. All right, so things will be a little bit different here because of the presence of the battery. So we're gonna again write the current to flow this way. That's gonna be our I also as a function of time. And the flow of the current this way will increase the charge on the left hand side of the capacitor. So I'm gonna write plus Q here. And obviously the other side will be minus Q on the capacitor. And in this way, it should be clear to you that when you have positive current, meaning that current flowing this way, then you're gonna have more charge on the capacitor, which is the other way around from what we had before. Right? So this will give some, like positive sign when you convert I to dq by dt. But anyway, the way we set up the equation is the same deal as what we had before, is to write down the loop for us to use the Kirchhoff rule. So we're gonna start here, and we're gonna walk around like this. Okay, so that's gonna be our loop. So using the loop again, the loop rule, going across a battery, you're gonna have positive V, right? So the first term is gonna be positive V0. Now, when we go across the capacitor, in this case, we're going across from positive to negative. So it's kind of like battery connected in reverse. So that's why we need a minus sign here, minus VC, okay, instead of plus. And this is because we go from positive side to negative side of the capacitor. So essentially, you can also look at it this way. So this battery and this battery, which is actually a capacitor, kind of go against each other. So they kind of cancel out. Or not cancel out, but you know what I mean? They have the opposite sign. So if you go like plus and plus like this, that's wrong, because that means both batteries go in the same direction, where in this case we don't have that. Okay, so you need a minus sign in front of the voltage across the capacitor. And then you go across the resistor. So that's going to be minus I times R, and that's equal to 0. And that's the loop equation that we have from Kirchhoff rule. Okay, and the rest is just to write what we know from the definition of the capacitance. So the first is V0, that's the voltage of the battery. Is this better? Okay, all right. All right, thanks for letting me know. Sometimes I write and I kind of like unconsciously zoom out. So, okay. So V0 stay the same because that's the battery, that's fixed, right? Nothing changed. And VC is the voltage across the capacitor, so that depends on the charge divided by capacitance, like this. And minus IR. So minus I is going to be dq by dt times R. And it's minus sign in front, so it's minus sign in front. So there's no extra minus sign here, again, because the way that current is set up is when the current is positive, meaning it's flowing this way, it increases the charge on the capacitor. Okay, so again, this is my choice of writing down the sign of the current, right? Which is going back a little bit to the previous case. So here, in this case, the current is positive according to the reduction of the charge on the capacitor. So that's why I need a minus sign here. Okay, so the sign kind of like depends on the situation. So you have to understand like why in this case is it doesn't have an extra minus sign here. But anyway, this is another differential equation. It looks a little bit more difficult, but in terms of the way we solve it is exactly the same. So you can rearrange this and then move everything that depends on Q onto one side. So you're going to have dq and then Q minus CV0 on one side, and then minus 1 over RC dt on the other side like this. So this step is just rearranging, so there's nothing, crazy going on. So rearrange. But then we can integrate this, okay? The integration is kind of the same, but the limit of integration will be a little bit different. So I'm gonna write it like this. So we integrate this. I'll write another line. So we integrate dq divided by q minus cv0 equal to minus 1 over rc. Again, this is a fixed constant, so I can take it out from the integral. I have like this. And the limit of integration is from q at t equal to 0. And in this case, we are talking about charging a capacitor. So at time equal to 0, we can assume that there's no charge on the capacitor. So we can integrate from q equal to 0. And then integrate to some other time, which is q as a function of time like that. And then for time, it's the same deal, t equal to 0 to some other time later like this. Okay. Even though we have an extra term here, but when you integrate it, it actually gives the same kind of form, which is log of q minus cv from 0 to qt equal to minus 1 over rc from t equal to 0 to some other time like this. Okay, so I move the limit of integration here so that we can substitute it in the next step. All right, so I'm gonna do that now. So we're gonna have log of q as a function of time minus cv0 minus the same thing but with q equal to 0. So that's gonna be log of minus cv like this equal to minus t divided by rc. Okay, and again, if you have the difference in logarithm, then you can put them together, so it becomes a division. So it's gonna be qt minus cv divided by minus cv like this equal to minus t over rc. And then you can exponentiate both sides. So you can do that by yourself. Just make sure that in the end, so it's just algebra, so I don't want to, spend too much time doing something like that. So just make sure that you get this. Q as a function of time is cv0 times 1 minus e to the minus t over rc. Or if you want to use the same times constant, is cv times 1 minus e to the minus t divided by tau. And again, tau is the time constant defined to be equal to rc. So what do we have here? Well, it's not an exponential decay. It's kind of like, I don't know what's the exact word to call it. It's not also exponential rise, because when you plot this, it's exponentially going up, but it's gonna reach some value in the end. So looking at this, when times goes to infinity or approaches infinity, then this term will be very small. So you're left with only the term in front, which is CV. So that can be drawn like this. So it's kind of like what we call in mathematics like the asymptotic line. And that's equal to CV. And the time, another time, the graph gonna looks like exponentially approaching that line. So that's Q as a function of time here. Okay, so this is the charging effect. So right at the beginning of time, t equal to 0, you have no charge on the capacitor. And when you wait longer and longer, you're gonna have more and more charge. And eventually it's gonna approach this value. Okay, and that's when it's fully charged. And that kind of makes sense because as time goes to infinity, like Q when t goes to infinity is just equal to C times V. And Q equal to CV, that's the definition of the capacitance, right? So that's no surprise that it gives you this kind of value, right? So most of the time, when you're not, worrying about, this charging effect, like what happened in between, you just look at the end result. Like the end result is you charge the capacitor with this battery. So in the end, the charge on the capacitor will just be C times V0 like this. Another interesting that we can write down is the current. So the current in this case again is just dq by dt. And by calculating this, you're gonna get V0 divided by R, right? Just differentiating this function. Again, you can do this yourself. You're gonna get e to the minus t over tau. So the current will exponentially decay just like what we had in the previous case, which is for discharging. And that's fine because in the end, when you have no change in the charge anymore, then you don't need to have any current, right? So the current is associated with the change in the charge on the capacitor. So if you don't have any change in the charge, well, current will be 0. So in this case, the current gonna exponentially decay to 0. So the initial current is V over R, like this. Okay. So I, which is the current, is the slope of the charge. Right. Similar to, remember the first semester when you have the velocity, which is the derivative of the displacement. It's kind of the same thing. Right. So you can see that the slope here getting lower and lower and lower. So the value here is also getting lower. So it's consistent with our definition of the current here. Okay. So the way to calculate, like the charge or anything in the current. Sometimes, again, we don't care really like what happened in between. We care only about the end result. So for the remaining 5 minutes, then I will talk about that. So you might be kind of presented with this kind of question, right? So but I mean, we're gonna talk about sample question again when we do the review. Let's say we have like a battery here, and we have two capacitor in parallel like this. Okay. So we have two capacitor, C1 and C2. And then we have the battery like this. Okay. So you can see that now with two capacitor, the equation that you need to solve, the differential equation you need to solve, becomes a lot more complicated. But sometimes the question asks about what happened in the end. For example, what happened when time goes to infinity, and not interested in the time in between. So in that case, you can actually ignore like the time dependence stuff and just ask yourself what's gonna happen in the end. Well, what's gonna happen in the end is that the capacitor C1 and C2 will be charged somehow, and there will be no current flowing because when everything is settled down, you have no movement of the charge. So you don't need to worry about current. So at time equal to infinity, no current in the circuit. Okay, because there's no movement of the charge. So when there's no current in the circuit, the voltage V0 here is the same voltage across C1 and C2. Right. So if you want to find out what is Q on C1 and Q1 on C1 and Q2 on C2, you can simply say Q1 is just V0 times C1 and Q2 is V0 times C2 like this. At the end, when time goes to infinity, like this. Right. On the other hand, if you're interested in at time equal to 0, what happened? Well, when time equal to 0, there's no charge on the capacitor. So the capacitor is just like they're not there because there's no charge. So no Q on each C. So right at time equal to 0, the circuit looks something like this. Because there's no charge on the capacitor. R1 and then R2. Okay, so in this case, you can calculate what's the initial current. So I simply equal to V divided by R total. And that's just R1 plus R2 divided by R1 times R2 times V0, like this. Okay, so this is kind of like a simple way of answering this kind of question, like what happened at time equal to 0 or time equal to infinity. Is you can answer this kind of question without solving the differential equation. Okay, but anyway, if you want to know like what happened in between, then you really need to solve this differential equation. Okay, so that's the time that we have for today. Again, let me remind you that we're gonna have a session on Saturday from 10 a.m. Okay, so if you can join, then I will see you there. If not, then just look at the video later. All right. That's it for today. So thanks for today's session, and I will see you again on Saturday. Okay. So take care, everyone, and see you later.